The Technical Training Department of Yaskawa America Incorporated presents Servo Basic Concepts, an overview of applications and guidelines for successful use. Hi, I'm Steve Kaler. Now, most people who are involved in the world of technology have heard the word servo before. And while most have heard the word, many aren't familiar with exactly what it means or how a servo functions. If you've seen an industrial automation system in operation, you've seen servos at work. To fully understand automation, it's essential to understand servo operation and application. And that's what you'll get out of this training program, a practical overview of AC servo systems and how they are used. We'll define what a servo is, examine its components, and explore how it works within a motion control system. We'll examine some of the most important concepts used when applying a servo, including axis of motion, system power-up, directional movement, over travel, distance and position, homing, and actuators. Here's a basic definition of a servo. It's a device that produces motion in response to a command, then regulates the speed and direction of that motion in response to feedback. You'll find servos in use on automation systems that require motion with precise control, and especially in systems that need very swift response to commands and exact fidelity to position requirements. The world of industrial servos is a very diverse one. Some servos are hydraulic, some are pneumatic, and others are electromechanical. In recent years, industry has moved more and more toward the use of AC servo systems. AC, of course, refers to the alternating current waveform in the motor during operation. The AC servo system involves two basic components, the servo amplifier and the servo motor. The servo amplifier takes in low voltage commands for torque, speed, or position, then amplifies them into a high-powered format that the servo motor can use. A servo motor is much more powerful than other motors of the same size. Powerful magnets make servo motors exceptionally quick and accurate. A feedback device called an encoder is built into the servo motor at the back end. Now this is an example of an optical encoder. It's a disc mounted on the motor shaft. As the motor rotates, small photosensors detect lines on the disc. The electrical pulses from the photosensor are sent back to the amplifier. The amplifier uses the data to control the motor's position, speed, and torque. Now we have some insight on what a servo is, but we haven't yet described how a servo gets things done. We put a servo to work by making it part of a motion control system. At the input to the servo amplifier is a controller. The controller provides the commands that dictate when and how the servo motor will move. The controller sends commands to the amplifier in the form of an analog signal or data. The controller and the amplifier also exchange position feedback from the encoder. Connected to the controller, you'll find an operator interface. The interface is used to start, stop, and adjust the various functions of the machine. Interfaces can be simple buttons and indicator lamps, or they may be a more complex human-machine interface, or HMI. On the other end of the process, the servo motor is connected to a mechanical system that it moves, the servo mechanism. This is a common example, a simple linear actuator that translates the servo motor's rotary motion into linear motion, in this example using a screw. This is only a simple example. The mechanisms used in industry can be complex and diverse, depending on the job that needs to be done and the imagination and expertise of the machine builder. While these 5 components exist in every motion control system, some manufacturers have designed units that combine one or more of these components. This is an example of a unit that includes both a controller and an amplifier. Combining components means fewer parts, fewer connections, and a smaller footprint, and greater convenience. The term axis is one you'll hear very often in this industry. Each servo and the mechanism it moves counts as one axis of motion. This word axis is drawn from mathematics and the concept of axes in a Cartesian coordinate system. Here's another way of looking at it. Imagine that an Etch-a-Sketch toy was controlled by two servos. One servo would control the up and down direction, the other the left and right. Now that would be two axes of motion. In this example, the two axes are mechanically connected together to create two-dimensional motion. But even if there's no connection, each servo is considered an axis. Now this distinction is important because in the world of industrial automation, a single machine may have several servo axes, sometimes even hundreds of axes. Regardless of the number, there are some fundamental ideas that apply to each axis. And here's one of the most basic. An axis will provide no motion unless you turn the servo on. Turning on a servo isn't as simple as switching on a light bulb. It's important to know that there are 3 stages to enable a servo. First, the amplifier itself must be turned on. We refer to this as control power. The system is typically wired to power up the controller and the operator interface at the same time servo control power is established. The second stage is to apply the high voltage and high current power source that the amplifier will use to drive the motor. We refer to this as main power. The main power input allows flexibility in wiring to the servo amplifier. The third stage is to energize the servo motor. We refer to this as servo enable. This signal to enable the motor comes from the controller. Servo enable doesn't mean the motor is moving. It only means that it's ready to move when commanded. Before the servo is enabled, the shaft will easily move. But if you manually try to turn the shaft while the servo is enabled, it will hold its position. You may hear a hissing sound as the servo works to maintain this position. After the servo motor is energized, the controller typically requires the operator to press some type of a start button. At this point, the controller will command motion according to its program. This particular controller is programmed to move the axis in both a forward and a reverse direction. To do so, it needs to define what forward and reverse means. What is considered forward for the servo may turn out to be reverse with respect to the machine. It is important to match the servo direction with the machine direction, not only for programming the controller, but also for any other features in the servo amplifier that are sensitive to direction. For example, the servo may use a protective torque limit in one direction, but not in the other. I can manually overpower the motor in one direction, but I can't overpower it in the other direction. So you can see why it's important to understand which direction is forward and which direction is reverse. In some circumstances, this could create catastrophic damage to your machine if not properly configured. Another direction-sensitive feature found in amplifiers is overtravel. Some people refer to this as the limit switch function. Overtravel is an amplifier input that stops the motor from moving in one direction. One input for forward and another input for reverse. We establish the boundaries of overtravel by placing a sensor at each end of the machine's range of motion. A properly programmed controller should prevent the machine from ever getting close enough to reach these sensors, but experience dictates the wisdom of planning for the unexpected. Overtravel inputs can prevent costly damage. Without it, moving parts of the machine could be allowed to crash into one another. Now, the positive overtravel sensor is connected to the amplifier input that stops motion in only the forward direction. The negative overtravel sensor is connected to the amplifier input that stops motion in only the reverse direction. So you can see that if these sensors get switched around, or if the direction of the servo doesn't match the direction of the machine, the motor might not stop at the overtravel sensor. Damage or even injury might result. It pays to remember that an overtravel stop is not an emergency stop. An emergency stop would prevent all motion in all directions. An over-travel stop is simply a quick way to stop motion in one direction. In an over-travel condition, the controller can be programmed to recover and the servo can still be moved in the opposite direction. While the servo amplifier and servo motor are the devices at the heart of the motion control system, let's move our discussion upstream to the controller, where all the commands originate. The topic of controller programming is beyond the basics, but we can cover some fundamentals, like distance and position. The program may require the servo mechanism to travel a certain distance relative to its current location. This is called a relative move, and this approach is helpful when programming a move that needs to repeat itself several times. On the other hand, the program may have a preset table of positions to which the machine is to move. In this case, an absolute positioning move to a certain position can make programming the controller a lot easier. Now here's an example. If you order me to take 3 steps forward, well, that's a distance command, a relative move. If you tell me to go to the table, that's a position command, an absolute move. It's the same result, I'm at the table, but the type of command is different. Modern industrial motion controllers allow the programmer the option to define the move either relatively or absolutely, whichever makes the most sense for that particular part of the control program. For this reason, we really can't tell which method was used by simply looking at the machine in motion. Absolute positions and moves only make sense when compared to the absolute position which the controller has identified as 0. The machine requires a repeatable method to find this 0 point. This method is often called homing, or 0-point return. To reorient an axis that may have been moved while the power is off, the controller needs to home each axis every time the machine powers up. A very simple way to accomplish homing is for the operator to visually align the axis to its 0 position. In actual practice, however, most machines rely on a fully automated sequence called a homing routine. Here is a typical homing routine in a controller. The axis first moves slowly in reverse, then stops when it detects a dedicated sensor known as the home sensor. We could use this sensor as the home position, but if we did, we'd need to physically move the sensor to calibrate the system. Instead, the axis moves a programmable offset distance to stop at a home position. Our final stopping point is then defined as position 0 for the controller's coordinate positioning system. Now, as long as the sensor remains in place, this homing routine will always put the axis back to the same starting point. Different types of machines require different types of homing routines. Programming a successful homing routine in the controller for non-standard machine configurations can be a considerable challenge for a controls engineer. Up to now, in our discussion of components, we have focused on linear actuators. They are common. They're also the easiest to understand. But there are many other types of mechanisms used in industrial automation. We can put the whole range of mechanisms in 2 categories: those producing linear motion and those producing rotary motion. For linear motion, the movement is defined in linear units, commonly inches or millimeters. A rotary actuator defines movement in rotary units, usually degrees. Now, within these 2 categories, there are 2 subtypes: finite and infinite. For example, a linear actuator has a finite distance it can move, but a pinch roll can pull material virtually forever. A rotating fixture with cables has a fixed distance it can move without twisting or breaking the cables, but a rotary table can keep spinning endlessly in the same direction. These machine characteristics are very important when you are programming because they influence how and if homing is performed, how relative and absolute moves are implemented, and whether or not over-travel inputs are used. There's a reason we call this program Servo Basics. It's only the beginning of the things you'll want to learn about servos and the extensive role they play in industrial automation. And a great way for you to expand your knowledge is with a visit to Yaskawa.com. It's a rich resource for technical information and product documentation, all searchable and ready to download and put to use. Well, we've come to the end of this training program, but it definitely isn't the end of our commitment to make Yaskawa drives and motion products the best in the industry. The commitment to quality continues in the way we work with our customers and with our vendors. It's in the way we train our associates. It means we deliver product on time. We answer questions quickly, and we never say we can't. Yaskawa quality is reflected in the effort our associates bring to work every day. To us, quality means doing everything we can to make our customers, partners, and employees' experience a great one. We commit to that. We make it happen. We can, because to us, it's personal.